Hello there. Today we'll be talking about the AsRef and borrow traits. This topic was requested to me by multiple people, both through YouTube and Reddit comments. So here we are. With this said, if there are any other topics you'd like me to cover, feel free to make a comment down below with your request. If your comment gets some likes or any other sort of endorsement to show that that's something people want to learn about, I'll probably make a video about it. Anyway, enough talking, let's begin. I think that the best way to understand how borrow works is to see it in action. So that's exactly what we're gonna do. First things first, I've brought the standard library's hash map into scope. You'll understand why in a second. Next up, let's create a hash map. And doing so, I want to explicitly say its type. So we'll say let, and we'll make it immutable. Call it HM. And its type will be of hash map string. And of course, we'll just say hash map new. All right. Now we can add a key value pair into it. That will be key for the key's key, and well, value for the value's value. Remember that is I will do an HM dot insert, and again key. This is currently a string slice, so we'll say toString, and value dot toString. Okay, and next let's just print the value of the key. We have to use this formatter because hm.get will return an option, and we will be getting on the key. Let's just run this real quick, and all right, no surprise, we got some value. Now it might seem subtle, but how did we manage to search for a string with a string slice? That is, why didn't we have to do something like get, right, and then pass in an own value? That's because in the standard library we have this implementation of borrow for string. That is, from a string we can get a string slice through a call to the borrow function. In addition to that, the get function for our hash map in the standard library looks something like this. That means that our key type, the capital K, must implement borrow for type capital Q, which is what get receives. That is, our actual type, capital K, can be borrowed as and consequently compared with our type, capital Q. If the utility of that isn't clear to you right off the bat, don't worry. It wasn't clear for me as well when I had just learned it. So let's walk through this step by step by creating our own smart pointer type like string to hold a string slice, implementing borrow as a string slice for that type, similar to how the standard library implements for string, and rewriting the hash map type to see how borrow is useful internally. In addition, all this effort will help us later on see how borrow and AsRef differ. Alright, like the title of the section said, we will be implementing our own smart pointer type, similar to string or box. Then we'll see how to implement borrow for it, and then we'll use that in our own implementation of the hash map collection. To start off then, let's decide how we want the user experience here to be. So fundamentally, we want to be able to define a, say, fake hash map, explicitly making its generic type something that we'll call, I don't know, my box. So similar to before, we'll say now FHM for fake hash map. We'll say explicitly its type, like I said, fake hash map. Its type will be my box. Hold a string slice. Same way that string, right, as a smart pointer that holds a string slice. And then my box for the value as well, which will also hold a string slice. Then we'll make a call to a an existing function called new. Okay, next up, we want to insert my boxes onto our FHM. So we'll say fhm.insert, and we will insert a mybox key before and a mybox value. After that, and probably the most important bit, is that we want to be able to get values from FHM using string slices. So we'll say println, and let's use this formatter, and we'll say fhm.get key. Obviously, we can't compile this yet because we're missing all the custom types we are making use of. So let's change that by starting to implement my box and implementing borrow for it. Okay, so my box is pretty simple to define. That is, all we want is a struct called myBox with a generic t. And considering we'll print it, we'll derive debug for it. Let's say derive, debug, and we'll say struct myBox, generic over t, and then we'll hold that t type. This way we can initialize it like this, right? Now, just like the standard library does for string, we'll do an implement of borrow as string slice from std borrow for box holding a string slice. So we'll say implement std borrow. This way you can tell where borrow is coming from. For my box string slice, similar to how we saw in that note in the first section of this video. And inside of this implement, like we saw previously, we'll want to implement the borrow function. It takes a reference to self, and in this case, as we mentioned, we'll be returning a string slice. So function borrow, reference to self, and we'll return a string slice. Oh, just something I noticed I missed, right? Right here, we have to say the type, right? Which is str. Perfect. Now inside of this body, we want to get access to the unnamed inner type of or my box struct. So we'll say just self.0, right? That's how we can access the first element of our unnamed type there. We're not really in a position to run this just yet, but we are getting there. Now let's implement our fake hash map. First up, let's create a generic struct over capital K and V called fake hash map. So we'll say struct and fake hash map generic over K and V. And obviously this is a fake hash map, right? So it will contain a vector of keys, we'll say vec type K, and similarly a vector of values containing V. Next, let's create a implement for our generic fake hash map. So I'll say implement kv for, or actually not for, implement fake hash map kv. All right. So looking back at how we want our users to interact with a fake hash map, we see that the first order of business is to implement a new function that returns a fake hash map, right? The first thing that we called in fake hash map new. So we'll say function new. Obviously, we want to be able to call it from fake hash map itself, so no references to self. Instead, we'll return the capital self. In its body, we'll instantiate a new fake hash map and populate the keys and values just with empty vectors. So we'll say self keys, let's use the vec macro, and values, again, vec macro. Okay, next up, we need a way to insert key value pairs onto our data structure. So let's create an insert method that takes a mutable reference to self, a key type k, and a value type v. Plus, let's not return anything in for it. So again, function insert. We're inserting, so we need a mutable reference to self, and then we're inserting a key of type capital K and a value of type capital V. Like I said, let's not return anything. And in the function's body, let's just push onto our hash map. So we'll say self.keys.push the key that we've received, and self.keys. Values, not keys, push the value that we've received. This way the indices of key and value are aligned, right? Lest, and again, most importantly, we have our get function, which will be generic over a new type that we'll call Q, and it will take a reference to self, a key, which will be of type borrow Q. It will return an option of reference V. So okay, let's put that into code. Function Q will be generic, a function get will be generic over Q, and it will receive a reference to self. This doesn't have to be mutable. And in here we have a K, which will be our key, right? And it is reference Q. In here, like we said, we'll return an option of reference V. Okay. That's not all though, right? Because we want, there are a couple of constraints onto our generics. K must implement borrow Q because, well, as we know, we want to be able to borrow our keys as a reference Q to compare them. And, well, Q must implement std compare equal, right? Which allows the comparison in the first place. So we'll say where Q, sorry, not Q, K, implements std borrow for Q, and Q implements std compare equal or equality. In the body of the function, we'll see how totally not ironically amazing our fake hash map is. So first, let's create a mutable variable that holds none. So we'll say found. You'll understand why in a second. Okay, so now what we'll do is a for in through an enumerated keys iterator, so we can have access to the index as well. So we'll say here for, again I said we'll have access to the index, right? So we'll say index item, and then we can do that with an iterator is we do in self, we're iterating to the keys, let's get its iterator, and then we can enumerate, and that's what gives us the indices. Now in here, in the body, we'll do a borrow of our item to compare it with the provided parameter. So this is the important part. Here we see where we use borrow, right? And the equality traits. So if item.borrow, so that's the item that we're currently at, we're borrowing it to compare it with K of type borrow Q. Right, and we know that K can be borrowed as Q. And here, if they are equal, we'll mutate found to hold some index So literally sum index, and break. Now outside of our for, we can do an iflet to check if the found matches sum index, right? The sum index pattern. So outside of the for, we'll say iflet sum index. This pattern matches found. Well, if it, oops, we don't want square brackets. So if it does, we can just return sum for a reference of the value at that index in the values vector. So now you've seen how amazing it is. So sum reference self values for the index. That's why before I mentioned that the indices of keys in vector will be aligned. Well, that's how we're searching through our fake hash map, but incredibly amazing. Anyway, if the pattern isn't matched, then obviously we just return none. With that, it looks like everything we specified in main is now defined. So let's try running it. Okay, looks like we got a couple of errors. Let me fix that and be right back. Okay, so from the looks of it, we just had a couple of misaligned curly braces, and I think I put a curly brace here after the option, so it obviously didn't catch the word properly. Anyway, now if we run this, we should get the errors that I'm actually expecting. So running it, there it is. It's complaining to us that string doesn't have a size known at compile time. And because of that, we have to relax the size restriction of Q. What does that even mean, right? So let's take some time aside to discuss that. First things first, what do we mean when we say something is sized? I've got an example here where I'm printing the size of some very clearly sized types to illustrate. Now, running this, we get 4, 8, 4, and 8 bytes. We see that that's right because the size of these types is literally in their names. That is, i32 holds 32 bits. Considering that a byte holds 8 bits, 8 times 4, 32, and hence we have i32. Great. Now we just heard that string, or the str type, isn't sized, right? Let's try printing its size with the same function. Just gonna copy this, put it over here, and change the generic to be this type. Now run it again. We get an error. No surprise. That's what we were expecting in the first place. And that's why we actually use references to that str type. That's why we have that string slice with the ampersand str. But, well, that aside, this error that we just got is actually very similar to the one we got before. Except, this one is kind of irreversible. So, we don't have any suggestions on how to fix it or anything remotely like relaxing the size constraint. Why is that? Well, as we know, str is a well-defined type. There's nothing we can do about it, but in our previous example, or in the previous code, the unsized problem was coming with our generic Q. At this point, it's important to note that the sized trait is a hidden trait for every generic we have. So, when the compiler says to relax that, it means that adding the question mark size bound to indicate that it may or may not be typed. To recap, I've brought back a snippet from our previous code, having replaced the capital Q generic with the type it evaluates to, which, considering we pass a string slice to the function, is str, right? That's string type. So let's take a look. Okay, so here you see that due to the hidden constraint of size that I've brought into view, we have a conflicting definition where we're telling the compiler that str is sized. Right, so this was our Q type. We replaced it with str. Same thing here. Obviously, this function is kind of doesn't really have meaning, right? This is a place for generics, but just for completeness of the replacement, we have str there. This is now a string slice. Returns my box string slice, right? A reference to it. And here we have string slice on the str type, which we know is unsized, right? As per our error, it doesn't have a size known at compile time. But due to the hidden trait that every generic has of it being sized, we have this conflicting definition. All right, now that we understood the error, let's go back to our code and fix it. All right, so now that we understand this error, and we also understand the compiler's recommendation, let's, well, listen to the compiler and add this relaxation. So let's go up here, and in the where for our Q, we'll say that it may or may not be sized by adding this marker. And now running it, we get some my box value. It all worked. So to recap, we implemented our own string wrapper type, which was my box that contained the string slice. We implemented borrow for it, similar to how the standard library does. So implement borrow as str for my box containing a string slice. After that, we implemented our own fake hash map type that we defined in our main function to contain my boxes. And we showed how we can implement a get method for our fake hash map that receives string slices to search through a hash map of owned my box types. All right, let's move on. If you look at the AsRef docs, you'll see that it's described as a conversion trait. So to give you an idea what that means, here are some implementations of AsRef that the standard library provides. So we can call an AsRef function on str to get it as an array of U8s, right? Sort of like UTF-8. Similarly for the owned string type and also string for str. On the other hand, borrow is described not as a conversion trait, but simply as a trait for borrowing. I think the confusion here happens because looking at implementations for AsRef, it feels like we could do all that we do with borrow with it instead. No? Or sort of vice versa. So let's take a look at the trait definition for AsRef and borrow side by side. So, trait, function, and generic names aside, doesn't it look like these two functions achieve the same goal? And while it might seem kind of underwhelming, it's true. If you wanted to, AsRef and borrow can be used almost interchangeably. So let's demonstrate that by going back to our example from before and see what it takes to convert our borrow usage to AsRef. Okay, so first things first, let's change from a borrow implement to an AsRef one, just directly like that. Now that we've changed the trait name, we have to change also the function name. Instead of borrow, this will be an AsRef. And to be honest, that's sort of it. The business logic of just accessing that element, it's the same. Next up, in our get function, we now also have to change our trait constraint for k to no longer be borrow, but AsRef. Okay. Now, is that it? Let's try running it. And surprisingly, or maybe not, yes. All we had to do was sort of plug and play our AsRef in. So after all this, what is the difference between AsRef and Borrow? The answer is that you have to look inside. The difference is you. The difference is me. The difference is us. The difference is in usage. The big difference is, in plain terms, that Borrow is used with generics, while AsRef is used with concrete or defined types. For Borrow, we want specific trait behaviors like quality and whatnot to work the same. After all, we're working with a blank canvas, i.e. generics. On the other hand, that might not be true for AsRef. After all, we're converting, not just borrowing, so sort of all bets are off. So the Borrow documentation provides an example that I really like. It says that, imagine we have a string slice wrapper that enforces case-insensitive comparisons. That is, for this type, an instance of case-insensitive string with a little OK does equal an instance of case-insensitive string with big OK. So, is it correct to implement Borrow string slice for our case-insensitive string slice type? Theoretically, it's fine. Conceptually, it's not, because our equality traits would be different. That is, little OK should not equal big OK. For example, think in terms of our fake hash map, right? If onto it we insert a case-insensitive string uppercase key with a type value of case-insensitive string uppercase value, if we do a get with a lowercase key, that will incorrectly return the uppercase value, just because that equality will work regardless of the case of string. So this is an instance to use AsRef. Alright, with that, that'll be all for this video, and I'll see you next time. Bye bye.